In the previous class, I had just introduced you to machinery vibration, and few takeaways from that was, we discussed about degrees of freedom, and then briefly introduced you into free response and forced response, and the terms associated with transfer function in terms of what is mobility, what is impedance, and then explained you or briefly showed you what experimental modal analysis is. And then towards the end, we saw the effect of damping, and then what are the different forms of damping, how damping can be measured in the laboratory. But then there are a few other issues in vibration, that is what we are going to discuss now in this topic on free and forced response of a system. When I discussed this body, I described it as by a simple equation Ft. Okay. When in condition monitoring I have a body, the question is who is giving this force. So, this force is because of an defect. Okay. And usually the frequency of this force defect is depending on its operational speed of the machine. I will give you an example. Imagine I have a shaft. Okay. It is supported on bearings. And this shaft is carrying a disc, which could be a pulley or a set of vanes. And imagine there is a big amount of unbalanced mass for some reason, because maybe this is a set of vanes and something has got stuck in the vane. So, and this is rotating with a frequency of omega f. So, if this unbalanced mass was m_e, this should be the force m_e omega f whole square r, where r is this distance from the center line. So, if I was putting a transducer on this bearing, it would capture the response on this bearing, but this response at this bearing will be predominantly at a frequency omega f, which is the operational speed of the shaft or the rotational speed of the shaft. So, what I wanted to prove to you is usually these defects occurs at the operational speed of the machines, or sometimes they are also known as characteristic frequencies. And if this response x will be dependent on omega f, omega n damping in the system. So, now in machinery condition monitoring or CBM, all we have is access to x. We may have some information about omega f, we may have some knowledge about omega n and damping. So, it is indirectly from measuring x or measuring x at many instances, we will find out whether a defect has occurred or not. So, this is what we are going to see. But then there are many instances where I have discussed this for a case of a linear system, but the same vibration will also hold true for a rotational system. Some external torque T. Okay. So, this is the rotational inertia. This is the torsional CT torsional damping, and this is the torsional stiffness, and theta is the response in angular domain. The theory which we understand in linear vibrations is also holds true, and like we had linear dampers, we will have torsional dampers. Particularly, we will see in many of the ships, etc., or many systems where there is a large propeller shaft rotating. To reduce the oscillations in the theta domain, people have put torsional dampers in the system. And now, here we will now introduce you to two other concepts. One is this base excitation. Suppose I have a body of mass m supported on stiffness k and damper c, and it is subject to the motion x 1 at the base. So, this body x 2 will react with a response x 2. So, if I look into the equations of motion of this, we will get something this expression. Okay. Now, you will see the response x 2 is proportional to x 1 times this term. Okay. And this is the equation behind the basics of vibration transducer, like an accelerometer. So, there is some motion in the base. How is this body responding is what we are going to look into. So, you will see in vibrations, you will always come across this term 1 plus 2 zeta r whole square, 1 minus r square square plus 2 zeta r square and square root. Okay. Many times in force excitation, base excitation, vibration isolation, you will come across these terms, and we will see what needs to be done. This is just to give you an example, okay, where there is a body of mass m supported on 4 springs, okay, and then they are all in and then we have this mass of 0.78. So, effective k, and then we can find out the linear natural frequency, okay. And certain conditions were given of acceleration to this body, and then you will see how this will react. So, this is can be numerically done, and then you can solve it, and we will give you an example wherein this scenarios will come in many cases. For example, I have a car, okay. I am not drawing the entire car, which is here. Suppose I have an electronic module, which is the engine control unit ECU. Okay, it's a very delicate electronic equipment. Imagine this vehicle is now going on an undulating road. Okay. So, this vehicle suspension system, there is, if you look into the suspension system, there is certain stiffness and damping present in the system, and it is there in all the wheels. I am just showing you one wheel. So, any motion coming from the road because of the road profile, there could be a wavy road or road full of potholes. So, as a designer, you have been asked to optimize the stiffness and the damping in the suspension system, so that the motion here x to t is the least, okay, so that this delicate equipment is not failing. Imagine, I will give an example. For example, we have small pins in this ECU. If you look at an ECU on an IC chip, there are small pins coming out. Imagine if this chip, which is which is a resident on this board here, if it is subject to repeated vibrations, there may be a fatigue failure, and this one of the pin can break. Okay. So, we will see an example how what is the allowable motion of this and so on. And this was the response of the previous case, wherein at resonance the amplitude shoots up. This is the example which I was going to show you. This is from the book by Inman. There is a wavy road, and the distance between these valleys is 5 meter, and the peak to peak amplitude is 0.02 meter. If the vehicle is going at certain v kilometers per hour, okay, and the vehicle has a mass of 1000 kgs and effective stiffness of 4 × 10⁴ Newton per meter and damping of 2000 Newton second per meter. The car's natural frequency in omega n is given by this. Okay. But look at the base excitation. The base excitation in the right unit is 0.01 is the amplitude sine omega rho t, where omega rho is dependent on the velocity v, right. So, vehicle on a wavy road. Okay. Prior to going to this, I will show you an example wherein we will see how this looks like. So, this is a vehicle going on a wavy road, okay, and you will see if my IC was here, what kind of motion it is being subjected to. And imagine if you are going on a wavy road, and if your vehicle IC is subjected to such large motions, it will lead to a fatigue failure, and this is what. So, we can design by effectively deciding on the K and C of such a system. Okay. So, you could have a different road profile. You could in this example we have taken a sine wave. It could have been potholes, or it could have been a trapezoidal waves. In fact, in actual proving grounds in test tracks, which I will show you, there are many such road scenarios wherein people. So, we will continue on this problem. See, if a car is running at 40 kilometers per hour, okay, omega rho comes down to 13.96 radians per second, and R is equal to omega rho, which is the external forcing frequency, by omega n. It comes out to be 2.207, and zeta is equal to this. And if you go to the very first equation, we will see if this is my x1, I substitute this. So, this is the displacement of 0.003 meters. Okay. A couple of takeaways from this expression is here x2 is x1 times 1 plus 2 zeta r whole square. and square root, okay, or I can refer you to the previous equation. This expression here. Okay. So, in the case of the numerical example, zeta is known to us, r is known to us, and then x 1 is known to us, we will find out x 2. So, as a vehicle designer, you will see that if we can play around with zeta, I can decide on the damping in the dampers of the suspension system. To play around with the stiffness k, I will and the natural frequency omega n root over k by m. I do not have any goal or any scope to change mass, but I can change k and I can change c, okay. And for any given scenario, I can find out x t. So, as a numerical example, all of you could do is, we took m is equal to 1000 kg. For the same road, say for example, if you are going on a bus, where maybe m is 10 times that, 10,000 kg, you will see that x t will be x 2 will be significantly less than even 0.003 meter. And all of you would have realized, going on a wavy road on a large heavier bus or a heavier vehicle, you will not realize this kind of displacements. So, this just gave you an example as to how one can play around with the damping and the stiffness to control the response. Okay. Now, another example which we will come across is what is known as a tuned mass damper system. By now, you get a feeling that whenever resonance occurs, there is a peak in the amplitudes. Okay. So, a tuned mass damper system is such that I can attach another body. So, this is my primary mass. I can attach a secondary mass where K p by m p is equal to K s by m s. Okay. So, that now it becomes a 2-degree freedom system. So, these amplitudes will reduce and natural frequencies would shift, and this has many practical examples which you will see. Okay. And this for a single mass system where we can work on the expressions here. And this is another example. Without mass damper, you see the natural frequency is shooting up. With mass dampers, the amplitudes have come down and frequencies have shifted. So, this is a very easy way to control vibrations at resonances. Many a times in torsional systems, okay, particularly in drive lines of vehicles, when there are excessive torsional vibrations, theta or theta double dot, people have attached torsional tuned dampers always as a fix to reduce this theta dot. Okay. And I will give you an example also, which is known as this is a demonstration here which you can see, but I will give you one other example is you would have seen high transmission towers, power lines. Okay, and then there are electrical catenary cables. Okay. Now, imagine if and then this continues and so on to the another pole and so on. Imagine if there was a large wind force. So, what would happen? These electrical conductors would sway in the wind, and it so happen their amplitudes of oscillation would be so high that one may touch against another. So, some sort of a touching can occur, and then you can see the consequence of a major contact of these two conductors. So, to prevent these vibrations of these cables because of large oscillations, what one does is one uses what is known as the stock damper. It looks something like this, and they attach it to these ends like this, kind of a dumbbells. Okay. Now, if you look here, this is which a stock bridge damper, sometimes known as a moose damper. It looks like the horns of a moose. So, there is a mass here, there is a mass here, there is a mass here, a mass here. Each one of them, and you can see an electrical cable here, and this is actually put onto the main conductor, okay, at one of these posts. So, in effect what happens, because of a large wind force, the cable would not vibrate, rather these would vibrate at their resonance frequencies, and these are usually designed for frequencies, which is predominantly, when somebody talks about wind forces, predominantly frequencies anywhere from 8 hertz to about 30 hertz or 40 hertz. Okay. So, tuned mass dampers, this is one example. Other one was I was giving you the example of a drive line of an automobile. Even you would have seen in large tall skyscrapers, okay, if because of large motions they want to move, if these motions are not desirable, we can have tuned mass dampers attached to such units. Okay. So, as I was telling you, vibrations has many effects, and if I was to list down, one was this free vibration. Free vibration occurs when there is no external disturbance or there is an initial disturbance, but it is this forced vibration which is giving an energy, because there is an external force, and the frequency of this external force is responsible for making the system run at that external frequency or the forcing frequency. And particularly in CBM, whenever we do the vibration measurements from any machine, we will see the frequency of this force vibration being reflected in the measured time history. And then few other cases, one was this base excitation, then we have the case of the tuned mass dampers, of course, the condition of resonance. So, we have to avoid resonance at all costs, okay, and all of them are influenced by damping. Okay. But then we will see, as I was telling you, vibrations is undesirable, but what if vibrations does exist? So, we need to see how can I control the vibration. So, at resonance, we can increase damping to reduce the vibrations. But we will see in many cases, what if there is a machine like a forging press or a hammer. So, each time the forging press comes down, it gives an impact force like this. Okay. Now, imagine this force will get transmitted to the ground and it will influence another machine, machine 2. So, this ground vibration of this machines has to be reduced by increasing the force by reducing the force. So, we need to play around with again with K and C, and that is what is known as the effective foundation design. And in the next class, we will talk about vibration and shock isolation. So, this is a view of this boost damper being tested in our laboratory, where we have electromagnetic shaker wherein we can generate forces and then see. We'll later on show you a video of this as well. Thank you.